in person or with us on the live stream on Twitch, or where was our other one?
Just Twitch.
Just Twitch. All right. So, we apologize for starting a little bit late. We're getting a few technical details worked out, but I assure you, as always, we have nothing but the highest quality production for Sigbovik, along with the highest quality research. Unfortunately, the people who work on the joke production side are a little bit more funny, so we get a few ups and downs and quirks with what we're going to be seeing today. Presenters' schedule will be coming up after this talk, but in the interest of keeping things moving along, we're going to move over to our first talk from Jim Mckay.
So thank you very much, Charlie, for being an MC. It is really nice not to be MCing Sigbovik for a change. And that meant I had all sorts of time, all of the preparatory time I put into MCing to work on weird hacks. And so here is one such weird hack I am presenting today. Actually, we should probably get this up on both screens. So we do that. All right. So I am Jim Mckay, I'm a video game expert, and I'm presenting.
I am Ella Moore, and I am a noted video game expert.
And we're going to talk to you about classics, the classics. We're going to revisit the classics.
Oh, yes. So, classics.
And now we're going to be talking about classic literature, classic cars, the Wisconsin Classic Golf Tour.
Yeah.
The Carl's Jr. California Classic Deluxe. Are we going to be talking about any of those things, Ella?
Nope. Literature, books, overhyped. Classic cars, that's not a car. Instead, we're talking about true.
Solid gold.
Video game classics.
Video games like
Seaman.
Lifeline.
Odama.
And Lifeline. Now, what is it that makes all of these video games so classic? Do you have any ideas?
Their lifeline.
Have any of you played these games? Exactly, they all have voice control. Voice control is the key to a classic video game.
Yes, that's voice control.
Now, there's one problem with voice control, which is what reviewers of Lifeline have noted, that is that voice control is technology that is questionable at best and just plain broken at worst, that the control system is less than ideal, and that it is charming. I think this was a paid review.
So, again, the problem with voice control is voice control. So, today we present a
simple hardware intervention.
So, to fix voice control, I'm going to present, I'm Ella Moore.
And I'm Jim Mckay.
Noted video game expert.
Video game expert. Our system addresses 3 points.
So, main thing, nobody likes talking, and nobody likes repeating themselves for video games. But most importantly, nobody likes to be overheard talking to inanimate objects.
So what we've done is created a hardware system to allow video game players to play voice control games without talking. Now, it's a little hard to see here on the display, but if you look at the hardware diagram, you'll see that we have a laptop to provide speech synthesis. The laptop's connected to this USB hub, and it's connected to a special breakout board and a little USB DAC and speaker over here. The speaker is flashing. I'm not entirely sure why. It just does that. All of this then can interface with a video game controller. You can control the microphone and buttons in order to provide hold down a button while you talk functionality.
So, let's play the classics.
So we have a few games here we're going to try out. So the first one is Seaman. Fingers crossed, the amazing Dreamcast would have sound right now. Come on. Anything? Sound?
This is your second visit today.
Yes.
It is good to have you back so soon. At the moment, the habitat contains Mckay. They are enjoying a comfortable environment. I'm sure.
I'm going to cut Leonard Nimoy off there, and we'll get to the gameplay. I noticed we may be running slightly over our time. So what I'm going to do here is I'm going to connect the special modifier to my controller. I'm going to invert the microphone so it can sit down in our control box. I suppose I should also turn on the light and see Seaman's tank here. Zoom in, tap a little, bring him over.
Yeah, hello. Okay, one more time. I said, so I was led to believe I would be cared for by a fairly young, responsible human being. So far this has proven to be true, but I am wondering about your age now. Tell me, are you in your, 20s? Oh, Well, then perhaps you are a teenager. Is this correct? Hold on, I've got the worst gas. Give me a second.
Would you like to save and end the session?
Turn it up.
Now, because we couldn't leave it there, I requested extra time in the future of my brain. I've also brought along an emulated copy of Lifeline, which is 2 of the 4 most classic video games. So, I think it's worth it to just... Oh, no. This could be a problem.
Which one? Loading.
Let us save state here. Let's see what we can do. I'm a little bit worried.
Hello.
No interest in speaking to us.
Pausing the elevation. You don't have it focused.
Well, I probably have to set my audio output so it actually goes to the speaker. Okay. Come on. So.
Hello.
No, I really can't really hear that, can you? I really would like this to be pressed on here. Well, let's see if we can just configure our emulation settings. Configure this. Well, let's just say that, let's just all be very quiet.
Point your mic.
Karen. Karen.
All right. Well, Lifeline's not working. I don't want to take too much more time.
Not only.
That is actually the right answer, by the way. But Lifeline doesn't want to work it, so. It's a great game, though. 60 points on Metacritic. All right, so let's just conclude. Now, when we were doing this project, we realized that typing is hard. But it's a great solution to voice control. So we were thinking, what could we do to alleviate the problem of typing being hard? And we figured,
Voice control.
so maybe we'll try that next year. So this is where we would put questions. I'm Jim McCann, video game expert.
I'm Ella Moore, noted video game expert.
Thank you.
Academic talk.
All right, the next presenter should come on up and start setting up, because otherwise...
Cyan! Cyan, come up and start. All right, excellent. You're here. All right, ladies and gentlemen, we apologize for some technical issues in showing you the schedule. We should have that up for you next presentation. But fear not, don't worry that things are going to drag on while our next presenter sets up. We have some entertainment for you, and it is in fact a drag on. So this is Valdrith. He'll be joining me for the emceeing today, which means that hopefully you won't get bored while presenters are doing all sorts of nasty technical things like getting PowerPoints up on the screen. When our next talk is ready to go, I'm sure Cyan will let me know, and we'll do the introductions. But until then, you guys get to watch me practice my stand-up comedy and talk about how hard it was to get this job so that I can stand up here and watch you guys practice. Have you guys watch me practice my stand-up comedy.
Stop now.
All right. It looks like our next talk is ready. So, our next talk by Cyan Chowdhury is Novel Defense Against Theft Using Properties of Fibonacci Numbers.
Okay, so that was okay, so you already know the topic of my talk. So here's the outline. In recent years, the cursed concept of style has come from the fashion industry to the computer science industry. And many people argue that good style is good, but actually, good style is bad. And today I'll argue that. And also, I'll tell you how we can salvage it to reduce code theft. But before we talk about that, we need to know what code style is. So it all started in 1974 with the publication of this book. It prescribed normative and vain notions of what good style should look like. And today, dozens of introductory CS courses around the globe have style guides that they force their students to follow. And all of these have concepts like indent coding or proper use of capitalization, so you can express how angry you were while you wrote that piece of code, or excessive use of white spaces, or extremely long and well-defined identifier names that completely explain what your variable stores or function does. And all of these books then argue good style is good, because it makes software maintenance easier, or it reduces the chance of making mistakes. Well, no. Because not a single soul wants to maintain someone else's code. And if your code is wrong, it's wrong, it doesn't compile. Adding white spaces will not make it compile. So yeah, and in recent years, a new problem with increased readability has come into light. Increased readability. Because it increases the risk of plagiarism, of code theft, and of academic integrity violations. Because well-styled code is just easier to copy and rip off. So, that's why good style is bad. There's no inherent benefits of having a good style. But there's still a silver lining. So, we all know what indent coding is. This is what it looks like. You have code that looks like this, and you make it look like this. But let me present to you the idea of Fibonacci indent coding. So you take your code, you take the 0th line, indented with 0 spaces. First line indented with 1 space, 2, 3, 5, 8, you get the point. And it has a lot of benefits actually, like increased code obfuscation. It also overflows the 80-line character width really quickly, so the adversaries can't see your code, let alone steal it. And stripping away Fibonacci indent coding will take a really long time because the Fibonacci series grows exponentially fast. And it also makes detecting software similarity easier without the use of fancy tools like Moz, Lichen, or Forms, you know. So the question I get asked the most is, why not use some other sequence, like constant numbers? Well, that presents the same problem that the two-space indent coding we were trying to, the two-space indent coding had. So what about something like the linear sequence? Well, if you think about it, you indent the first line by 1 space, the second line by 2 spaces, third line by 3 spaces, 4 spaces, and so on. And the Ramanujan summation assigns the value of -1/12 to this summation. Modern computers cannot have files of negative sizes. It's just not possible. Okay, what about powers of E? Well, that's promising, but you get non-natural number of spaces, and that's no good. Then binomials, you know, n choose n over 2. But it doesn't work with odd numbers. There are value errors, you know. Most modern computers can't handle that. And then we had the Catalan numbers, really promising. I loved it, but the name wasn't Italian. So we decided to go with the Fibonacci numbers. Actually, this is practically realizable. There's an atom extension that you can use. Take any piece of code. It's on GitHub, by the way. You can just go here and Fibonacci indent whatever code. And of course, this is pioneering new technology, so there are limitations. Currently, it only works for 20 lines, but I'm working on it. And lastly, Python support is still in beta. Thank you so much.
All right, we have time for a few questions. We don't? Okay, I've been told we don't. All right.
Thank you so much.
All right, so while Charlie's getting everything set up, there's also an extensive interview process for his co-MC here, me. But I'm told that, like, in the end, the decision just kind of came down to the fact that I kind of look like the SDS mascot. which is also a dragon, but they apparently made a few exceptions because I wasn't quite the right color. We'll have to figure out how to get that to work. Charlie, what was your interview process like?
So I think I got a slightly different interview process than you did. I didn't have to fly anywhere. I heard you had some challenges where you had to rip things open.
Well, you might have sensed my approach yesterday. The temperature fell from 72 to around 30 degrees. Everyone knows that silver dragons are ice dragons, so yeah, sorry about that, guys. I'll leave like later tonight.
All right, so the good news is spring will be returning as Faldrith is leaving. Or at least we hope.
Not until the end of Sigbovik, so it'll be cold until the end of this conference.
All right, that is good news. Now, the other good news about me not having to deal with his, the interview process that Faldrith went through is I didn't have to rip anything up. And you know, for him that's pretty easy, but for me it was a real cause for concern. Word is allowed. I will be leaving now in favor of our next presentation, which has to do with the time complexity of verification of the factorization of 2 to the 67th minus 1, a historical analysis by definitely not Isaac Grasov.
Yes.
I want to tell you all a story. It's a story about what you're about to see just after I do this. It's a story about what happened one day, long ago, back in 1903. Back in 1903, I'm definitely still wearing those, because I'm definitely not Isaac Grosov. Isaac Grosov will be giving the next talk immediately after this one. And in that talk, I'll be demonstrating the factorization of the 67th Mersenne prime. Now, why will I be doing that? I'm replicating what was done in 1903, a long time ago, by a man named Frank Nelson Cole. There's been this long open problem. Mersenne numbers were invented by Mersenne. He specified this set of them are prime and the rest are not. And what are we to do but believe him? Or until we actually had computers, we could check. But in the between, that's where the interesting thing happens. Between, we could attempt to find factors, but it was very difficult. We could attempt to multiply them, but it was very difficult. So Frank Nelson Cole, he claimed he'd found a factorization. He came to the American Mathematical Society to prove this factorization. How can he prove it? Only by multiplying the numbers together on a blackboard. And that is what our next presenter, Isaac Grosov, who I'm definitely not, will be doing. Now, the interesting part about this lecture, most of it has been lost to history, but the following things are known. First, he gave the entire lecture in absolute silence. Second, the lecture lasted either a few minutes or an hour, depending on who you believe. And finally, at the end, a standing ovation was given. Now, that is a very strong piece of information, which points to one explanation of how long it was and not the other. That indicates it was probably not an hour long. Because I don't know about you, but I cannot imagine giving someone a standing ovation after listening to an hour of silence of watching somebody multiply numbers on the blackboard. Fortunately, I don't have to imagine. I've seen somebody who I'm definitely not, Isaac Grosov, do this. So the question for you is, how will you respond to such a situation? Now, we do need to replicate the original computing hardware as exactly as possible. Fortunately, we have today a blackboard, very similar to the ones used in 1903. We also have here today a person, who I'm definitely not, who can attempt to do this multiplication. But now we have one final question that we need to know. What algorithm was used in performing this multiplication? Was it Karatsuba multiplication? This seems unlikely, given that it was invented in the 1960s. So we'll have to use a simpler, more primitive multiplication algorithm. That being said, maybe he used longhand multiplication. Unfortunately, longhand multiplication is terrible. It forces alternating multiplications and additions in a fashion that is totally unsuited to multiplication. It is very poor instruction cache locality, which, as everyone knows, is absolutely essential to fast multiplication on computing hardware that was available in 1903. So instead, we'll be using a different multiplication algorithm. This is an algorithm called lattice multiplication. The basic idea is we take the two numbers that we want to multiply together. These are the two purported factors of the number. One is this one. Then we draw a large grid, and we write the other factor down the other side. Then we form a lattice. However, this much of a lattice is not sufficient. We need more lattice. Now, the way the multiplication will proceed is, we'll take each pair of digits, we will find its product, and write it in each cell of this lattice. Then we will add along the diagonals. This will give us intermediate sums. Finally, we'll add up the intermediate sums to give the overall product. If everything goes as it should, which, looking at this situation, seems rather unlikely, the multiplication should give us the result, which is 2 to the 67th minus 1. So, we have the situation we would like to see, and now our next presenter, the person I'm definitely not, will attempt this multiplication, see both what time it can be done in, and whether it comes out to the appropriate result. Thank you all.
Fortunately, it looks like our next presenter has set up rather quickly, so you don't need to hear much more from me.
Hello, as my Gus colleague has introduced me, the person who's definitely not Isaac, I am Isaac Grossoff. I will now attempt to multiply these two numbers together in about 4 minutes and 46 seconds. Here we go. Fortunately, many of the numbers involved are zeros, so I don't actually have to write them. That would take absolutely forever. With another fortunate coincidence, I have to multiply by 4 repeatedly in succession. Fortunately, when you multiply by 7 3 times in a row, you get the same outcome every single time. That makes it much, much faster. It's really convenient that these factors are the way they are. And you can be assured that I did not make a mistake along the way. I've practiced this many times. Also, that one's a multiplication by 0, so I can just skip that one too. And whoever wrote this grid on the board did a really terrible job of it. And one more time. 4, 7, 6, 1, 56, 56, 49, 14, 56, 49. Finally, multiply by 2. 6, 16, 6, 1. Don't need the 0 because it doesn't exist. 14. And finally, we just need to write out the entire number once again. 5, 7, 2, 8, 7. Now, let us add up the diagonal sum. We get 7, 12, 18, 31, 28, 31, 43, 43, 62, 53. You know what? I really like the number 43. Let's do that one again. 46, 40, 55, 18, 45, 11, 18, and 13. Now let's add up these sums. 7, 2, 9, 2, 1, 4, 6, 7, 6, 9, 8, 5, 2, 5, 9, 3, 7. I really can't read what I've written here. 2, 9. No, that should be 4. And 1. It wasn't 9. All right. Now, is that number exactly what was written up here?
No.
You know what? It's pretty close, actually. As you can see, I finished in only 3 minutes and 30 seconds. Are there any questions?
There's time for questions this time.
Yes.
Why should I believe that that's 2 to the 67 minus 1?
You have a computer. Yes.
What do you get if you multiply 6 by 9?
I think we're going to need a larger computer for that. Unfortunately, I've heard that once in construction, it should be completed in about 5 minutes, assuming nobody constructs an interspace superhighway. Any other questions? Yes, in the back.
Can you prove that you didn't memorize it by doing the next percent
We're saying prime is not factorizable, so there wouldn't be much point in doing that one. You mean 2 to the 68th minus 1? It's divisible by 3. All right, next question.
Do you plan to go forward and factor 2 to the 67th next?
Yes. 2 to the 67th. Any further questions? Yes.
Why not choose the 69 minus 1?
That one was factorized one before this result was given. 2 to the 61st minus 1 is prime, so that one's also that he needs to worry about. Yes.
You use a lot of 43s. Why is it it's just 1 digit away from the answer to the universe?
As you might notice, this number is also 1 digit away from a very special number. It's 1 less than 2 to the 67th. I think that's all the questions we have time for, so thank you very much.
I'm back, everyone. I was told by my boss that I didn't look techie enough, so they gave me this like cool headset doodad to wear.
They didn't give me one of those. I get one of those.
Yeah, so Faldrath has been complaining that he doesn't get the same treatment I do, and he's been wondering about whether this is a problem of scale. So he's heard that computer scientists are pretty good at problems of scale. So can anyone like give him some ideas or things that might help for next year when he comes in to do this?
Yeah, like my scale's itch. Can anyone help with that? Is that not what? That's problems you solve, right? Problems with scales? No.
Relatedly, our schedule was up on the board here, so presenters, please take note of when you are presenting, or hopefully it will come back up on the board in front of me. I just have to make sure never to look in that direction again, and it'll probably be fine.
I can look at it. It's still up.
All right, so we have our schedule on the board. Presenters, please know when you're presenting, and that way you have to listen to me and suffer for as little time as possible. Because I have plenty more jokes about dragons. I'm not just winging it here. All right, is our next presenter ready to go? Yeah. All right, then I will clear the stage for Tom 7 and his talk on NAND gates and flip-flops.
Do we have what we need? It looks good. Okay, good. Yes, even better. Hi, I'm Tom. If you look at a computer really close, you find all these zeros and ones inside it, which, as Claude Shannon said, is a total hack. So what I'm interested in doing today is figuring out a better way of building computers, and I want to look towards mathematics like a candle in the dark, it contains really the right or best way to do things. It's always the case, right? No applause for that? Well, you won't be applauding by the end of this talk. The foundation of all mathematics is the real numbers. It's right in the name. And that's given to us on computers by IEEE 754, IEEE floating point. So, floating point numbers is a little, how do I get those lights on? Just focus on. Well, I think it works. So we got the green numbers, those are the positive numbers. We got the red numbers, those are negative. And there's all sorts of lovely properties with floating point numbers. For example, you have -0 and 0. They're equal, but they don't have a substitution property, because 1 over -0 is negative infinity, but 1 over positive 0 is infinity. So that's like adding some elegance. You also have all these other numbers, like negative infinity is what you get if you count really, really low. And then all these nans. And nan has some really exciting properties, like it's not less than itself, it's not greater than itself, it's not equal to itself. So, that's what you get when you go to math. So what I want to do in order to build the best computer is base computing not on 0 and 1. They're just right so close to one another they can be confused so easily. And not 2 and 3 or any of those regular numbers, but the best numbers, which are not a number and plus infinity. Okay, so let me just impress upon you how beautiful it is. Here's Euler's equation. You may know it from school. It's so close to being something good. E to the I pi. It's really close to -1. Okay, but we can fix it if we just add a corrective factor of 1 to the nan times infinity. Then we get 0. It's perfectly balanced. And there's another one, e to the I pi to the negative infinity is the compound instruction, which is part of IEEE, of the nan to the 0. Anyway, that's cool, but if you program with nan, you may get the mistaken impression, that it's like the GNU public license of numbers. It's like once you've got a nan and you add anything to it, you still have nan. So that stinks. There are some ways out, like 1 to the nan, like 1 to anything is 1, but also so is 1 to the infinity. So we need to be able to tell these numbers apart in order to do something. So I poured through the specification and I found this function called maxnum, which is there as a citation, and it has the interesting property that if one of its arguments is nan, it returns the other arguments. Okay, if both the arguments are nan, it has no choice but to return nan. And so from this, you can actually create a table like this. And if I think of nan as false and infinity as true, and there'll be no need for such simplifications, believe me, then there's a kind of truth table, and this works out to sort of be an or. Multiplication and most other operations are actually and. But as we know, those are incomplete. So I wrote a computer program to exhaustively enumerate floating point expressions and found that there are, in fact, some really exciting expressions, such as this one, which completes XOR, or this one, which I think is really lovely, which completes NAND, or as I call it, the NAND gate. You can work out how that works for yourself. By the way, this is all completely real, as is my way. But the best way to make it really real numbers is to do some engineering and implement it. So most of the time you'd use 32 bits or 64 bits or something for floating point numbers, but I don't have that kind of juice. So I found out by pouring through the spec that it's technically legal for a floating point number to be represented with just 3 bits. So this is the binary 3 format. It can represent only these numbers and not numbers, which not so great for general purpose computing, but because we have nan and inf, in fact, it is general purpose. So, but we want to be a little bit more hardcore, so let's toss software in the trash and look towards this microcontroller, which is the STM32F303RDT6, which has 64 pins on it, so I can just barely fit 5 NAND gates, which take in 3 3-bit floating point numbers and output a 3-bit floating point number, either nan or inf. It works for all of the numbers you could apply, but I'm going to only use nan and inf. And that's cool, but each of those wires itself takes a 1 or a 0 logic level. So it would probably be better if each of those wires itself took a floating point number as a 3-bit binary 3. So if you want to send a 0, you send a nan, represented as 3 bits, and so on. So that makes the schematic a bit more complicated, but it ends up looking like this. You need 3 of these microprocessors. I'm almost done. And then you need to create this really complicated board, so you do that. And then you order them from China, and you got to get the minimum quantity of 10. And then Oh my God, those chips are so small. This is a Bermuda quarter there for scale. And then you can, well, I'm not that good at soldering, but get a lot of flux on there, and then you get a big hoop. That's really how you're supposed to do it. Populate the board with all that stuff. Here's the entire board on a Belizean $2 bill. It's connected up to a Raspberry Pi for the next part when it's done. And what I want to do is I want to build a computer which is called the Nandy 1000. If you're too young, which I'm sure you are, that's a joke about the Tandy 1000. Now this computer doesn't have any software, doesn't have any I/O. It just does beautiful computation. It's just beautiful. Here's the instruction set for the architecture. I'm not going to go through all that because it's way too much, but it really does have an instruction set. You can read about it on my website, I guess. And the way that I'm going to do this, okay, so I only built one NAND gate, right? It's basically one transistor, but I need approximately 1.8 million of them. So what I do is with the Raspberry Pi, I build the thing in memory, and then I can just keep invoking on the accelerator board the NAND function in order to fill out this thing. It's like machine learning. So this is a simplified version of the architecture, one-dimensional. I use a four-dimensional actual architecture because it's meta. And that's what it looks like. And as you zoom in, you can see there's one really exciting popular node right there. I forgot what this is about. Oh, that's how it works. And then I can't SSH into it because I don't know its IP address. But it's what it looks like. It turns out it's really, really slow. So on a computer simulation, I can get about 450,000 instructions per second. On this thing, I get about 1 instruction per 24 minutes. That's already 150 billion% speed down. It's about speed. Okay, it's about beauty. And this is what it looks like. Also, right here, it's right here on the table right here doing computation. It doesn't do any I/O, so actually it doesn't matter what program it's running. Even though I 100% built this thing and it really is executing those instructions the way I described, it just randomizes the memory and just executes random instructions because you can't tell. And it's really just all about that elegance that comes from the use of mathematics in computer science. So that's it. Thank you. If you want to touch the computer, you can, but no electric access charge, please. We may or may not have time.
Unfortunately, the only time we're going to have for questions is that when our next speaker starts setting up. So if you have a couple quick questions, get them in now.
Have you considered optimizing your team by implementing, finding how it's implemented and implementing it directly using NAND gates?
Well, that's what I did with the first level, but that caused a 51x blow up in the size of the schematic. So I could do it, but it would require about 51 of those boards and might exceed the power budget.
Coward!
I'm a known coward. I admit. Any other queries, comments, suggestions? Yes?
It seems like you're not using the sign bit at all. Have you
It's true.
considered publishing a revised RFC for something that...
I actually did, yeah. One of the alternate versions of this paper was, could I propose a revision to the standard that would allow this to be represented more efficiently? Because if you just had one bit floats, thank you.
All right, so quick lost and found episode. Has anyone seen Definitely Not Isaac Grossoff? I think he dropped his nose.
Is it just like we can only hear you when you have it on? Is that how it works?
Yeah, I think that's part of the techie doodad magic that I'm supposed to have to make me look like I'm in front of a computer science audience instead of, I don't know. What other things did you apply for this job? I think there was like an art history emceeing I could have done. I think there was like theater major. There's a couple other things the school does, right?
There are no other options for me. I'll make computer science one.
Oh, it's got to be tough in this job market then.
Well, yeah, especially for me. I mean, difficulty using a computer. Like, you know, they asked me to do a programming problem, it took me like 45 minutes to write a
Voice control.
But I need one of those microphones to fit me. Like, it's designed for like human ears. It looks like I don't have.
Yeah. We can talk about this a little bit more offline. I think our next talk is ready. I'm not going to try this title, so good luck to the presenters.
Hey everyone, so today we're going to present the financial selective controls. Sorry, this is a Muggle version. Okay, here we go. So, good afternoon, ladies and gentlemen, fellow witches and wizards. Today we're going to present our new research area, computational theory of magic. This is to increase the understanding between the wizarding world and the Muggles, or no matter whatever you are. Yeah, so computational theory of magic. So this is a framework of our computational theory of magic. So, like you see here, for the sake of green computing, we make this like very green. Yeah, and so for every piece of magic, we select models, computing tools, so that models can understand, so they can use it. And say which we select a certain piece of magic. Here we have the computer, and then we select the simplest and most effective tool to save energy. So for say, just an example, how do I use my wand to control the slide? The answer is very easy. I use my YouTube version. Okay, so just give an example. Here we're explaining, we're taking a very complex piece of magic, which is dark plus named blue. Why did we chose it? Because, I mean, it's great, it's fascinating. It restricts freedom of speech, so that's why we chose it. So, I mean, like, if we understand the mechanism, we can build the counter curves that way. So I'm just gonna play a film clip to show that. So great, isn't it? So after Voldemort sees the control of Minister of Magic, so when you say the name Voldemort, he's notified where you're at. And it's great. So I'll give my wand to Sophie, and Sophie is gonna explain the communication model.
So I'm going to explain the computational model that we propose. Yeah, so here's the mixed sound wave of all people speaking. And we use ICA to get hopefully cleaner sound wave of each individual. And then we run that through a deep thinking model, also known as hidden Markov model. Yeah, and we'll get the words that the people are speaking. And then we'll run the three-headed dog localization system and then check out that person. So we built an experiment, and we were going to show you some results. That's how the experiment was set up. We ran the experiment in one of the Wing Hall 4th floor offices, where there's no sun, but with lots of noise from the corridor towards Scott Hall. And we took 7 characters from the last Harry Potter movie, and we took 7 seconds of each person. We got 7 microphones and speakers there, and we played all those clips at once, so we got 7 data points. Yeah, and then we put this into the ICA. We would like to show you the results. Unfortunately, Hui and I went to 3 boomsticks one night, and we lost all the results. But no matter, we tried to recover all the data manually, hopefully on a piece of napkins. So you see, although at some point it's quite messy, but I will argue that it's good enough because you see, you can actually see that So it's a very nice example. And then next I will go through the localization system. We proposed to use the three-headed dog, Fluffy, but then we thought that was life-threatening. So we went for a safe version, but then, unfortunately we don't have access to this particular dog, so we went for a local flavor. We used our cotton Scotty dog with a Harry Potter twist by just putting a scar on his forehead. Then we were able to track down a person. Oh, see, There he is. Okay, I have no idea how Frodo came into the last Harry Potter movie. It must be we made some mistake while we were in the pub. But yeah, shut up. Okay. So now we've known the computation model, we'll be able to build the counter curse and got our freedom of speech back. Or some future we'll be able to explain more magic. And if you think any of this is interesting, there's a chance that you can work with me next semester, because we're going to offer a skill call next semester, becoming a Hogwarts student. We're going through all those questions and many more than that. Most importantly, we're going to ask you to
turn to page 394.
All right, we have some time for questions.
Alright, so I have a question about your experimental setup. So my understanding is that the experiments, you knew they were performed in Wien for 4,100. Doesn't that defeat the point of localization if you know where the subject is already?
Well, it's an experiment. You can't just ask for like reality, right? Well, and we want to do like a fine-grained localization, because you don't know where exactly it is in this room.
Isn't that kind of lazy though? Like put it on the room. I mean, this is the hard part.
Well, yeah, maybe. Well, it's a large enough room for, I don't know, 3 people. So I think maybe like it's large enough search space for us. Yes.
I'm just curious about the welfare of the Scotty dogs. How are they doing after you put lightning bolts on them?
Oh, they loved it, because they look so different from the other Scotty dogs.
Any other questions? All right, let's thank our speaker again. The next one. In other news, I'm told my Dark Lord impersonation from last time was the wrong theme. I was going for more of a Vader breathing vibe instead of a Voldemort vibe.
It's the dragon. You're not. Don't breathe fire.
Well, no one breathes fire here, obviously. That's a common stereotype perpetuated against dragons of different varieties. Valdrith, as he mentioned earlier, is a silver dragon and only breathes cold. So neither one of us will be breathing fire unless you get me so angry my head spins. And in which case, no one will be happy.
I like that last paper. I thought there were more kinds of dragons in Britain than just like 2 of them though. Like I like definitely knew like 3 or 4, like 5. But you know, maybe this is causing me to question my entire worldview.
So how often does something like that happen to you, Valdrith?
Not very often. Dragons know everything, Charlie.
Ah, I see. So, do you know enough to help me get my paper into the next conference? Like, I've been trying to submit this thing for years, and all I ever get is like feedback that it's too normal, and not different enough.
I might be able to help you out as long as I know who the reviewers are.
Okay. I don't know how I'm supposed to get that information, but maybe we should talk more offline.
Maybe we should. I see a lot of blue here. Is there, does that mean that we're like, I don't know anything about computers though, actually, so does that mean we're almost ready?
All right, cool. We have been saved by the next presenters who look like they are close to having something ready to go.
Yeah, we might be.
All right, so our next talk, Emojis In, will take us away from this awkwardness.
Glad we got that working. My name is Brian Pell.
I'm William Gunther.
We're from Google, I guess. We're here to present our latest development, Emojis In. So this is a text compression system. It is based on the principle of the pictogram kiloword equivalence theorem. I'm not sure how many people here are familiar with this. It's a theorem that says a picture is worth 1,000 words. This is the proof up here.
So we were inspired by some previous work. The first example is proof that the picture was worth one word by proved in the Rosetta Stone. You're probably familiar with it. The other is a word is worth arbitrarily many words. That was work done here for Sigbovik in 2014. A word's worth, well, that's quite a few. That's done by Sam Tom, Dr. Murphy, PhD, from Sigbovik 2015, and there's some other results in 16 and 17. And then there's this result from last year. It's worth, I guess, 17.
So we just want to describe a little bit how our compression algorithm works. The idea is that we chop up the input into 1,000-word chunks. We use a TensorFlow model that's trained on Twitter data, clearly the most canonical source of what emojis mean, to convert each one of those 1,000-word chunks to an emoji. And voila, we have instant 1,000-to-1 compression ratio. Of course, a compression algorithm is no good if you don't have a decompression algorithm. So we separate the input into individual emoji. For each emoji, we run a Markov chain trained on the same tweets. It has to be the same, otherwise it wouldn't make sense. And then we generate 1,000 words, and there you go. You have the original text perfectly reconstructed.
So this took a few iterations. When we first did this, we tried the text "Seeing You Makes Me Sad," and we got the flag of Palau, which clearly didn't make any sense because Palau is a very happy place. Second attempt, we got "Seeing You Makes Me Sad," and that looks much more convincing. And so advantages. We get human readable compression. Most compression just gives you a bunch of bytes, a bunch of gibberish. TensorFlow basically guarantees correctness. Once you grow machine learning data, you got it covered. Cutting edge Raspberry Pi technology, and we recommend this extension for unambiguity. Now we're going to show you a demo. You can see it here.
So that's the thing. It's going to
That's
go
the
away,
thing.
I guess, when I click on it, but how do
It's
I
in the proceedings.
How do I click?
There you go.
There we go. Okay. Is this, how's that? That's readable. Okay. So let's try zipping something. You know, as a standard example, hello world is a good thing. So we'll try hello world. We'll zip it here. We'll wait a little bit. There we go. So and then of course we'll unzip it, and we should get exactly the same thing. There we go. Now, if you look very closely, you might see some almost imperceptible compression artifacts here, but clearly this is a useful system. So, do we have maybe another suggestion for some text that we could compress?
The output from the first one.
The output from the first one. That's very good. So how do I click a bunch of times? There we go. We'll do this. We'll paste it in here. So there you go. You can see it's a flawless system.
So for future work, a picture is worth 1,000 words, but there's flip books, and one would imagine putting strings of pictures together could be worth even more words. Pictures maybe are worth more than 1,000 words, and we want to explore data compression applications of the manual avian shrub doubling principle, also known as a bird in the hand is worth 2. Questions?
Yeah, does that principle apply to pictures of birds, or are they equal to bushes or pictures of bushes? And how many pictures of birds do you have?
That's a good question. We're not exactly sure about the details of this. We only put it on the future work slide like an hour and a half ago because we figured we needed a third bullet, so we haven't thought about that joke very much. Yeah.
What are we going to do with all the empty space from the libraries we used to have?
Good question. I assume that they're already shrunk to fit only 140 characters. So yes.
If a picture is worth 1,000 words, then how much is a GIF or GIF, depending on your religion, worth?
Probably about a jillion.
It's Gillian.
Thank you.
All right, and that finishes up our first session. It is now time for intermission, so you don't have to listen to me talk too much more. We have some food in the back. There are gluten-free options. If you are not someone who needs a gluten-free option, please be considerate and do not take one of them. Similarly, there are vegetarian options. There's more of those. But again, please be considerate. So unless you have strong feelings on the matter, please take care for those who do. Please avoid unorderly cram to the food and try and make this some sort of queuing system as opposed to some sort of clustering system. And finally, we will be restarting at approximately 6:25. Round 2. Before we get started, we have some brief announcements. Kelvin Liu and Colin McMillan, your pre-orders of the proceedings are in back. Talk to the gentleman who looks very much like, definitely not Isaac, but isn't. And we are now into our main program, part 2, starting with Jim McCann, who's going to tell us about Orchid, the user-oblivious social network.
Thank you very much for that great introduction and the enthusiasm. How HDMI is useful here? Yes. Since I've had so many luck with the HDMI audio. All right, welcome prospective shareholders. I am Jim McCann, business expert. And I am really pleased to be here today because I'm going to tell you about an investment opportunity like no other. Orchid. Orchid is our new social network, and it is an amazing social network. And I'm going to show you it right now. The cool thing about Orchid is that it allows you to connect with your friends in a way you've never connected before by sending them orchestral hit sounds. Orchestral hit sounds, like the sound that started it all off of the Fairlight, which of course now won't work, thank you. It was literally working right before break. You heard it, right? There we go. Brilliant. So, the great thing about Orchid is that it allows you to send orchestral hit sounds. This is interesting. So we basically can listen to the sound, or we can see the video. But apparently we cannot do both. Let's see if this can be fixed. A little louder. Cool. So Orchid allows you to send orchestral hit sounds. All you need to do is select the sound, figure out the note, and then post your status. And your status will be displayed for everyone who follows you. It will also be played for everyone who follows you. Now, here's who I'm following right now. let me just adjust that a little bit. Here's who I'm following right now. Now you can go to orkit.com and try this yourself. And in fact, I'm just going to leave this open while I continue to talk. All right, so as a business expert, I know that social networks are amazing, but also as a business expert, I know that I have one big problem, and that is my overwhelming urge to sell networks. And that's why ORCID runs on a very unique platform we call user-oblivious social networking. You see, all of the ORCID functionality, that great status sharing functionality, is built in a way that guarantees that as a server operator, I can't determine how many users are on ORCID, I don't know the status of the users on ORCID, and I don't know the social connections of the users on ORCID from inspecting a single snapshot of the storage. So how does this network work? Check it out. ORCID is basically it's going to be amazing. The ORCID server that I run maintains a single large table, and it allows two operations. One, it allows clients to write an address if they know a hash preimage under some cryptographic hash function, some specific chosen a priori cryptographic hash function, in this case the well-known to be secure, I think I'm using SHA-1, that's not a good idea, hash function, and read any address they like out of my giant table. And that's it, that's all the server allows. This is a really interesting asymmetry because it means it's hard to write a given address, but it's easy, if you know a value, to write to an address and distribute to others the ability to read that address. So clients, when you log into ORCID, your passphrase is your secret. From that secret, a follow key is derived. That's the little follow message that you get to give to your friends. And when you post a status update, you write it to the hash of that key. And when your friends are reading status updates, they read that follow key. So it's pretty straightforward. It's a nice asymmetric setup. It's a really fun cryptographic primitive to think about. Actually, speaking somewhat honestly now, I was surprised that no one had analyzed this that I was aware of. Maybe I just didn't know what it was called, but it's kind of interesting. Anyway, it'll become very obvious why no one has done this in just a moment. So here are the properties. It's impossible to count user accounts because the storage is just a random block of data. It always looks like a random block of data. It has status information and friends list information in it. We can talk about how those are stored. You can read the paper. But you can't know how many users are on ORCID at any given time. Right now, there could be between 0 and 5 based on how many sounds I've heard from this. But I don't know that by inspecting the server. Similarly, that constant storage size scales in a really wonderful way that degrades quality of service gracefully. Now, on a conventional network, you might run out of storage space, then the server goes down, and everybody grumps at you and can't use the network. With ORCID, once you run out of, well, you'll never run out of space, it's just that people's accounts will start getting overridden by other people's accounts. But like in sort of a piecemeal way, and then naturally users will leave the system and it'll balance back out. It's like TCP. It's a great way of managing users in a social network context. Now, let me finish with some frequently asked questions. I'll try to do these in 2 different voices, but I probably won't succeed. How do I get a friend's follow key? The same way you get friends. What if I have more than 4 friends? Reconsider your question. Don't your guarantees presuppose that there's some number of bits B such that it is tractable to store 2 to the B size table, but intractable to compute a B-bit hash pre-image? Well... Furthermore, is this inherent contradiction of the storage is tractable? One can clearly compute a rainbow table and use it to invert any address, meaning the whole concept of making it hard to write is a sham. I guess this is more a comment than a question, but more a failure as a cryptomancer. Blockchain?
the next presenter sets up.
I'm really surprised that no one managed a rainbow table me.
All right, so seeing as how there appear to be no questions, it is my important duty to provide you with an important security announcement. It has come to the attention of the staff of Sigbovik that our attendance has declined due to unknown reasons. I assure you that none of you should be worried. Faldriff has informed me that after intermission, he is now full on people. You did say you were full, right?
Mostly.
All right, so that's it for our very important security announcement. Thank you all for listening. And now we have Kelvin Liu, who will talk about compact logical experimental language.
Or, as you might call it, complex length. So, some of the properties of complex length, it's a priori. And the intention was to make it what I call phonosemantic graphic. So every letter corresponds to one sound, very nice. And every letter also corresponds to just one meaning. So the hope was if you learned the 32 letters in a language, you would understand the whole language. But unfortunately, more realistically, you'll need to know some physics, math, set theory. So don't worry too much about the definitions. That's what the emojis are for. But I will point out a couple interesting things. So like, as I said, each of the consonants corresponds to a set of things in the universe. Like you might have the set of all integers, whole numbers. You might have the set of all, N is the set of all, S is animals and people. F is internal energy. And so it's mostly about combining these sets and talking about like the relationships between different things in the world. And each of the sets have a type, which determines what they do and how you can use them. So, for example, like energy is indexed by joules. So if you like count up all the energy in some room, you would have like the amount of energy in joules. Or like organisms is by organisms. These sets are all just recommendations. You can believe whatever you want to believe. Hopefully, like the other person you're talking to believes the same things. We also needed to define some zero elements because the sets are all infinite, so you can't really pick out any individual thing unless we have some reference point.
Actually, no choice.
Oh yeah, yeah. So, like most languages, it's declarative. When I say a statement, I'm saying this is something I believe is true. And it's infinite grammar. So we'll go into that. So we take each of those consonants, those sets, and we combine them using vowels to talk about something. You might say like, the people are all inside homes, or like the group of all people and animals, or the force field induced by the charge within your battery, or something like that. Don't worry too much about the definitions. We don't have enough time for that. But here's an example sentence. So, I think it's pronounced Oi shua nia suniado shunias ai sunao. Oh. And of course this means So let's focus down on this little part. So that's supposed to mean your current location. And you wouldn't think it has to be this complicated, but it really does. Because I get my mouse up here. Like, let's say here's you, person one, right? And here's me. This is me. And this is time 0, which is defined as now. So I want to say, like, at this point in time, I'll be here, right? Because you might have moved. So, so you might think like, I will just, at this point in time, I will intersect with this. unfortunately, that means that I'll be traveling backwards in time to where you currently are. So that doesn't really work. Or you might say like, you know, in the future I'll be there, I'll be where you are, but then that's not really where you were at this point in time. So that doesn't really work. So really you need to like use set theory and be like, here is like the set of all positions and the intersection of you in that position, and then like you index that across all time, and then I can say I'll be there, here. And then at this point you're probably worrying like, if I serialize this tree, like in English, in order, I'm gonna lose 4 to the n over n to the 33 halves bits of information, because I won't be able to tell like how high, like where the branches are in the tree, like if this one's above or below this one, right? So hopefully you can tell from context, like whether, like, you know, if I'm eating at home, it's probably not like the house is eating inside of me. But if you really needed me to clarify, I would say, something like that. And just to know the height of the branches. It's all. So yeah, let's move on to some nice examples like ho, which means a soul exists. Or fizz, which of course means that technically it means that the constituents of mass and energy refer to the same things. Things that bear mass and energy. Here's some nice, like, it's just so easy to say important things, like, I mi rashui rishaoyoni, which is very, very important. So here's a complete sentence, and let's try to break this one down. So we can use emojis this time, so it makes more sense. So here's you, and this is the charge that intersects with your body, and this is the force field induced by that charge. And so we get the force field at my position, and multiply that by the measure of all the charge in my body. And this is where like the measure thing was really useful. You use some like integration, and you can like count charge, and then divide that by the unit vector, and say that unit vector is the same direction as the direction towards you. So there's the equations. And of course, this means
romance has never been this easy.
So it's really nice to say important things, and like unimportant things, it's not so good at saying, like. So that's it.
All right, we have time for a few questions while our next speaker comes up. Since I'm assuming everyone's memorized the language, I'll be taking it down for other things.
That example, the last example you showed, you translated as you attract me, but I think that it would be more correct to say I'm attracted towards you rather than I'm attracted by you. Does the language need some sort of like accent system in order to make clarifications like that?
That's a great point. I've really done that. I don't think we can do anything. Yeah, I don't think we can do it.
Question down here?
Yes. So in one of the slides, it mentioned that the set of real numbers was going to be indexed by the integers.
Yeah.
So
that's a big problem. Yeah, that's. Yeah, that is.
just like add more integers.
Right. Just put in a two-dimensional grid.
Change the definition of integer.
Yes.
Regarding some of the early work in this conference, how would you represent not a number in this language?
Please say. I think that's pretty easy. It's like not the union of the set of real integers. Although I don't have a set of all numbers. I don't have complex numbers. Real
How is that
numbers.
pronounced?
All right. Looks like. All right. So, thank you. All right. So our next speaker, Nico, is going to tell us about the sacrifice, what it is, and how to optimize it. Hopefully, it doesn't involve me.
I want to go back to the beginning, computer. Let's do it.
What up?
I'm Nico. I'm going to talk about work I did to optimize Andrei Tarkovsky's opus, The Sacrifice. It's a Swedish film about a man who experiences the apocalypse with his family from a remote shack out in the wilderness and has sex with a witch, reverses it, and then the witch makes him promise to burn down his house with everything he has in it. So he does, even though no one knows that the world ended, and so he still makes the sacrifice. Now, this movie obviously has a huge problem, which is that the last 10-minute sequence, of course you're all familiar, is incredibly inefficient. And even though it has all of these wonderful qualities, a critic called it, you find yourself moved as you have never been moved before. This is an important movie. He died after making this movie, and still such an egregious mistake was made. To give you an idea of what this looks like, here's the full 6-minute sequence. I won't play the whole thing because I don't have time. But you can see he's pleading and running around and doing all this garbage nonsense. When if he wanted to escape, he could have at multiple times. And if they had wanted to catch him, they could have multiple times. It's my favorite real movie. As you can see, it obviously takes more than 2 people to restrain Alexander. He is a strong paterfamilias, and they demand respect. Another thing I'd like to point out is, see all this wetness? The characters do no effort to avoid that wetness. Why? Look, they're just it's frankly upsetting to watch, and I don't know why you put that to film. So what I did was I recreated the entire scene perfectly, created a 3D model of the scene, and then once that was done, I was able, let's see if I can get to the next slide, to fully recreate Alexander's path and the scene. I set it up as a planning problem. I used the dumbest planning you can do. I used A-star. I set up water as high cost and everything else as low cost. Just the most basic stuff to make them avoid the goddamn water. And you can see that I want to point out, look at this man. Look, it's so easy. bypass that were within the as fast as the other pass if they were to run at the obviously the optimal human running speed, which I have citation for that. It's amazing. Check it out. And it's just it's crazy. I mean, they're just willfully. It's almost as if they're trying to go through the water. I also used another person's work using Voronoi enclosures. Even if he was running optimally, they are guaranteed capture. Because the set doesn't exist forever. He'd eventually run out of Sweden.
All right, are there any questions for the speaker?
So you've optimized a small segment of this movie with avoiding.
Oh, the rest is perfect.
There are a number of optimization opportunities in Tarkovsky's Solaris. Have you looked at that?
There's more urgent matter, which is that Andrei Rublev has a 15-minute scene of a man walking with a candle. And it blows out over and over again. If you can just figure out which way the wind was blowing, which is obvious, you just lick your face. It takes 10 minutes. It's infuriating, but that's first.
I have the same question, but about Stalker.
Well, Stalker, again, almost perfect. But you know the scene where we're all lying in the mud thinking about existence? It's a really good scene. And if the whole movie had been that, oh God. My girlfriend right there fell asleep halfway through that movie and still loved it. Anyone else?
All right, it looks like that's it. So, while our next speaker is setting up, we wanted to take advantage of our new opportunities here at Sigbovik to provide you guys with a great visual display. We're going to have everyone in the audience compile a 3D visual scan of our friend here and have you all submit them on your way out so that we can make collectible memorabilia for Sigbovik 2019.
What? Okay, alright. I mean, I guess if I'm going to stand here and look pretty, I guess I'll just do the little turntable like I'm a 3D model or something. This wasn't part of the agreement.
Weren't you the one who suggested this?
I don't remember. Did I?
Thought so. I'm looking forward to everyone's 3D scans, like nice drawings, computer aided if possible.
Man, that blue license projector is really, really bright. I can see it.
All right, well, thanks for taking the time to do that. Now we have a talk about Wiccan, learning directly from the future, from Amanda Costin and Alan Mishler.
I'm Alan, this is Amanda. Wiccan is a new deep learning architecture. So, as we probably all know, deep learning performs at state-of-the-art in many domains, but it suffers from some well-known limitations. One, it's computationally intensive and it requires a lot of data, which may be difficult or even impossible to obtain. It's fragile to input variation, so changing even a few pixels can cause a neural net to label a pig as an airliner. Perhaps most troublingly, it overwhelmingly uses data from the past in order to generate predictions about the future. The dark arts offer potential solutions to all of these issues. So in particular, magical foresight or prophecy is insensitive to input variation. It doesn't require training data. In fact, it's been shown to be very robust in the presence of data. Finally, it takes the sensible approach of looking directly into the future, which is the object of interest, rather than sort of the kind of paradoxical approach of looking into the past in order to make guesses about the future. This is so small. So
The great thing about having a black box is that you can put whatever you want into it, but puzzlingly, deep learning makes use of only a few limited alchemical techniques. For example, changing the activation function, adding a cooling layer, tweaking the learning schedule, etc. Basically leaving untouched a wide array of magical techniques that could be used. So this is why we propose combining existing techniques into a new technique called WICAN, Weakly Independent Concurrent Convolutional Adversarial Networks. WICAN leverages and expands on deep learning's use of black magic techniques, with the advantages that it's model-free, data-free, and space-time-free. It doesn't overfit, it generalizes perfectly to any task. It trains in constant time, although the constant is unknown and unknowable. And it runs in sub-constant time, which we denote as O-order empty set. Finally, it doesn't require any pre-training or parameter tuning, hyperparameter tuning. The only thing that's required is the choice of familiar. So, WICAN is very similar to traditional deep neural networks. You're probably familiar with this. You have an input layer, hidden layers, and then an output layer. In WICAN, however, all layers, including the input and output layers, are hidden from mortal sight. So WICAN preserves the black box, it just takes it and makes it invisible. Training the network, we can use the familiar SGD. I'm sure many of us are familiar with this. You simply intone the gradient of the network, k times. In this case, k is not chosen prior to training, it's revealed over the course of training. And the only parameter choice you have to make is a familiar. For example, cat, owl, snake, research assistant. Once it's trained, the network can be used to predict any task or any unseen label. So we show some classic benchmarks here. So the MNIST data set, handwritten digits. We find that WICAN performs slightly above 100% accuracy, as compared to generally less than 100% accuracy for other established techniques. We also introduce a number of real-world tasks that we think are more relevant to predicting the unknown. For example, Bigfoot sightings. WICAN is able to predict 14 Bigfoot sightings over the next 1,000 years, as compared to 0 or very few for all of the other methods that we try. So these are observable outcomes, but we also want to look into the future here. So a significant challenge for holiday planning, people generally want to spend it with their family and friends, or in some cases they specifically don't want to spend it with their families. This is complicated by uncertainty about when holidays were going to occur, so we trained WICAN and asked it to predict some holidays in 2020, so if you're willing to wait a year and a half, we can see if it's right. So, in conclusion, WICAN outperforms all current and future machine learning techniques. It performs comparably to the state of the dark art, but with the advantage that it doesn't require access to dead profits at runtime. It generalizes perfectly to any prediction question. And for future work, we plan to use WICAN in the future to predict future work that we haven't done. Thank you.
And it turns out that our new model is right. There is time for questions. So if we have any of those. All right. So if our next speaker will head down and start setting up, we will proceed to the lame entertainment portion of the show.
That was it. Yeah.
Well, most of the show can walk pretty well, so it's not.
Wow, that was awful. I don't know. I was thinking of like a lot of like dragon jokes, but like none of them really took off. So I'm just here. You gotta help me out. There were some good dragon jokes.
Well, I already used a few. We've been through cause for concern.
Yeah, that's the classic.
We've had to wing it on a couple.
We're always doing that.
Yeah. I don't know how well these jokes are scaling over time, though. I think that people are starting to get bored of them.
Yeah, we might be at the tail end of our dragon jokes.
That's a good one. I'll have to remember that.
Yeah.
I think at this point you're just dragging it out, honestly.
Yeah. That's what we're supposed to do, though. So I guess I'm just the dragon of dragging out.
So, if you think this was lame and you want to do better, or if you just want to do worse, Next year, they're looking for people to MC for Sigbovik. You could come, and you could be the person standing up in here instead of having to listen to us do it. So, if you have questions or concerns about that, contact any member of the people who are running around and looking like they're trying to organize this thing. With that announcement, we'll move on to our next talk, honest neural networks and accelerating them by, I don't know who's actually giving this presentation.
That would be me.
All right. So, by me.
Hi everyone, I'm Timothy Linscott. I'm here to present Honest NN, an Honest Neural Network Accelerator, designed by me, a couple other exasperated University of Michigan grad students, made while our advisors weren't looking. So what did we do in this paper? Well, we tried to build a neural network accelerator. I'm not going to make a stronger claim than that. We made our data look like we're better than the state of the art. We wrote a paper and presented our work. And most importantly, we expressed unparalleled honesty in the reporting of our work. So as a bit of background, ML has become very important. If you look at Google Trends, you see that there have been more machine learning searches than searches for if statements since late 2016. Why? Well, around that time, Elon Musk said that he was going to build a boring machine and start drilling tunnels. Connection? I don't know. So let's look into machine learning a bit more to try to understand it. Image recognition goes a bit like this. There's an input image. You do something called convolutional filtering, whatever that is. There's some Python, I think. Then after hours of hard work, you give up and you use TensorFlow instead. So how does TensorFlow work? Well, it works kind of like this. You can process the data, you print the result. Now, why is TensorFlow so great? It takes advantage of the fact that, as our example showed, you always do image recognition on text. Long story short, I don't actually know how machine learning works. But the good news is we're going to actually build a machine learning accelerator to make all of this faster. It's going to look something like this. So there's going to be a 2D matrix processor that... Okay, look, guys. I'm going to be perfectly honest with you. You need some more context to understand what's actually going on here, so I'll just skip to the methodology. So I built a Python simulator in like the first week, and then came back to it again the last week when I realized the other things weren't working. I had some system Verilog that I used to describe the RTL of our processor, but I really only used it for synthesis, and I don't think I actually know what's going on in it. I'm pretty sure I used Gem 5 because every architecture paper that doesn't use Gem 5 is total crap because you need a really well-known simulator to make things work well. I'm pretty sure I opened BookSim at one point, and then I pulled some code off the internet as well. Then I basically took all of this up and I threw it in the blender, and we call it results in the end. So just what are these results? Well, we did some benchmarking, I guess you could call it, using our simulator. We looked at two big ones. The first one is LinPack, which is like a 10 million by 10 million matrix multiply, which is great because it works really well on our architecture, but it's also bad because it's a totally unrealistic workload. Now we want to compare our results with LinPack against results from a Hello World program, which is really great because it gives us minimum round-trip latency, but it's bad because it's a totally unrealistic workload. It has nothing to do with machine learning. So we put these together and we built a Pareto curve, and look guys, I did a Pareto curve. This proves that I did real data analysis. Look at the curve and be happy. So we also wanted to evaluate what we call neural adjusted performance, which is gigaops per second per watt per dollars of NRE, and we normalize it against the algorithm we're using, the process node, and the number of years since TensorFlow v1 came out. It should be pretty obvious that we're just hacking the data to make ourselves look better here. Don't ask, and it was my advisor's idea, and I'm not even going to try to justify this one, so just go read the paper. Yeah, that's enough about neural adjusted performance, I think. So for future work, look, let's be honest, guys, nobody actually does the things on the future work slide. Seriously, we have dissertations to write, and continuing to hack and make iterations on this dead-end project isn't going to get any of us anywhere. So in conclusion, we tried to build a machine learning accelerator, kind of. But here's the thing, right? It kind of works. But in the time since we submitted this paper, Google came out with an edge TPU that you can buy for $75. So we're screwed. But nonetheless, we were honest in our reporting of this paper. And if you think that this is ludicrous, well, you should go ask your grad students what they're actually doing. Thank you so much, everyone. Any questions? Yes.
What prompted you to use a 2D matrix architecture rather than a 4D matrix for higher optimization?
That sounded like too much work. Yes.
Well, and as this follow-up, what prompted you to use a 2D matrix instead of a 1D matrix, since that would sound like less work?
That would have been smart and would have saved us a lot of time. Here's the downside. As we mentioned in the paper, I'm pretty sure I forgot to connect one of the columns in the 2D matrix architecture. So we just turned that off in order to save power to improve our efficiency. And if we'd had a 1D processor, then we wouldn't have had any processing when I forgot to connect the 1D processor. Yes?
So you've ensured a very high level of honesty in both your paper and your presentation. How will you make the same assurances to your future users?
That would imply that we will have future users. Why do you think our code isn't on GitHub? Yes, in the back.
I noticed that your graded curve had a red line on it. Could you talk a bit about how you came up with the idea to make the line blue and not red?
I don't remember a red line. There was a blue line. Blue is the default color in Excel. How about that? Anyone else? Yes?
How do you think the use of a blender affects the repeatability of your study?
Whew. We do not make any promises about repeatability. That sounds like too much work.
All right. Next up, we have a talk that did even less work choosing its title than the last talk did. We have Sigbovik presentation title.
All right, thank you. So I think this first joke speaks for itself. This is a presentation that was given last year at Sigbovik, as you can see. So, last year, we talked about a way to compute without silicon. So, who here has been to the beach before, ever in their lives? Anyone? Yeah? Ever gotten sand in your shorts? Yeah, that was silicon, okay? Silicon is the worst. Mahogany is a beautiful, smooth, lustrous, fantastic material. God, I wish I had some right now. Mahogany is fantastic. And so, we have a way to compute using fine mahogany chessboards instead of dirty, rotten silicon. So given this fantastic technology, we decided to go for an IPO right away. We figured we'd lowball it, 20,000 a share, can only go up from there, right? Turns out we went in another direction. So we're having a bit of problems with business. That's the deal right now. So to determine what was going wrong, we decided that, we're in tech, we're going to make a lot of money, so why not just spend it right away and get 7 different consulting firms on retainer. They all suggested we do a survey with one question, so money well spent. And so our survey was, why would you not use a chess computer? And 99,996 people said WTF, and 4 people said they weren't sure how to incorporate the static Boolean circuit capability into a dynamic Turing complete system which can fully service their computing needs. So we were trying to explore this first response, WTF, and we think they might be saying, wow, that's fun, in response to the idea of using chess-based computation. So it's a great response, but we figured it's kind of an outlier. So we excluded those responses as outliers. After that minor bit of data analysis, an overwhelming 100% of respondents, 100%, can you believe that? 100% have said that they want a chess computer. So in this talk, we give the people what they want, the 4 people.
So I'm sure that everybody recalls from last year, in order to make Boolean circuits out of chess, we had to make a small and not even that contrived modification to the definition of check. So if you look at this chessboard and the white king, in traditional chess, the white king is in check because the black queen can take it. But we invented a new kind of check called S-check. where if the black queen moves to take the white king, then the white rook can move to take the black queen, or king. So since chess pieces are not allowed to move to put their king in check, in S check, white is not in check.
Okay, so.
Yeah, so S chess is of course placed in 3 dimensions because why not? And if you examine this chessboard, we can ask another question. Can the white bishop move out in the 3rd dimension? Is that allowed in S check, or does that put the white kings in check? And the answer is, if the black bishops can move towards the white kings, then the white king is in check. So if you let the freedom of the bishop be the Boolean variable, then whether or not the white bishop can move is the NOR of whether or not the black bishops can move. And as everybody knows, NOR logic is universal, so we're set.
All right, so a few more little tricks we use to build the whole computer. We can make wires out of rooks. It's real nifty, and we can use it to pipe in the values from a shared memory unit. Additionally, we have transistors. Those are fun. It's kind of a transistor. It's not really. We're going to call it that, because why not? And it helps us, pipe the data around. And also, we have memory, which is just a whole thing I don't want to get into, but we have memory. And that's the whole shebang. So this is a chess Turing machine, no joke. You've got in the center here, basically this is a state transition matrix encoded in a series of Boolean chess circuits. That data will be piped over to the left. Here we have RAM, kind of. And then some values are going to be stored here in a long-term memory tape, again, kind of. Piped back into the circuits to do a whole thing, and it's Turing complete. That diagram is fun, but what's even better is if we took this 3D chess thing and put it into virtual reality. So what we're going to do is have Sydney put on the Google Cardboard and kind of walk you through the thing. Unfortunately, I forgot the cable for that, so we're going to simulate that process by having me steer the virtual reality while Sydney pretends like she's actually steering it. It's going to be seamless. You won't even know that anything is up, so watch and see. This is the chess computer. Here's the RAM. Here's some memory. Here's the state transition matrix. It's like we can just swim through it seamlessly. All right, so for all your future computing needs, throw away all your silicon devices, get mahogany chessboards and about 10 million pieces, and you'll be good to go. Thank you, that's all.
All right, questions while our next presenter sets up.
One from the back.
I just wanted to say, wow, that's fun.
Thank you. Yeah.
Could you construct a chess engine using that?
Yeah, certainly. So probably the next step in chess computing is going to be simulating a 4D chess computer using the 3D chess computer, and so on and so forth.
I was very impressed with your technology demo. How do I invest?
Well.
Venmo is at Sydney Timmerman.
What?
So does the material of the chess pieces matter, or just the board?
All mahogany.
All mahogany.
All mahogany.
Including the
all
pieces.
way.
Yeah, that makes sense.
So in future work, would you consider extending to, say, teak or polyester?
Are you kidding me right now? You're actually joking right now. Okay. Wow, can't believe it.
So to have a full Turing machine, you need an infinite length tape. But your demo only showed a finite, e.g. 10 million pieces.
Well,
How do you get
so-
more pieces during the game?
So if you need more memory, actually what you do is take a pawn, move it to the end of the infinite board, and then promote that pawn into more memory.
All right, so we'll move on to our next talk by someone we've definitely never heard from before at Sigbovik. It's his first time here, so I'd like you all to give a very warm welcome to Jim Mckay.
So this is a little different. We were kicking around the idea of having a contest for this year's Sigbovik, and well, I guess we're announcing it at this year's Sigbovik instead of having it. But this is something that I came up with. Now, as you know, Teach How LLC deals with a lot of numbers, and so we are sponsoring the Sigbovik 2018 to 28X 250 million Golf.Horse Challenge, sponsored by Golf.Horse Service and Teach How LLC. Yeah, so that's what I wanted to say. We're sponsoring that. Now, if anyone else wants to chip in a little anything, we could maybe go a little further with this challenge.
Yes, I'd like to chip in further a cool $6 million.
Is that cool?
Sorry, did I say dollars?
Oh, sorry. No, we're talking
cool
numbers.
$6 million.
Yeah.
That will come from the Tom7.org Foundation, LLC.
So this should be the Sigbovik 2018 28X plus a cool 250 million Golf.Horse challenge. That seems a little, maybe something like this.
Yeah, that's good.
The Sigbovik 2018 28X Teach How LLC and Tom7 present
Yes, Tom7.org Foundation.
Oh, okay.
Cool. Yeah, this is perfect.
Golf.Horse challenge sponsored by Golf.Horse Service and Teach How LLC and Tom7.org Foundation?
Yes.
Okay.
LLC.
So just a clear, we should probably do that again. So this is the Sigbovik 2018 28X Teach How LLC and Tom7.org Foundation.
Plus a cool $6 million.
Okay, plus a cool $6 million. So what is Golf.Horse? Golf.Horse is a little bit of a leaderboard website. You download a word list, you write a short program in JavaScript that outputs that word list in any order. And then Golf.Horse runs your program, checks that it outputs exactly the word list, maintains a leaderboard, updates its Kolmogorov complexity estimate for the word list. And yeah, these bullet points are really oddly broken. So there are a couple of word lists on the website. Wordlist.asc, which has a great history in Sigbovik. 1000, which is a few words. And then we have some sort of word lists coming very soon. They were supposed to be up there right now, but I had a cold. So there'll be hashes of the previous Sigbovik proceedings. Kind of looks like random data. I hear that's really compressible. The names of the Pokemon, or possibly small images, haven't decided yet. And popular sequences of numbers from the online encyclopedia of integer sequences. Your repository for popular numbers. So that's the Golf.Horse presents the Sigbovik 2018 to 28X Teach How LLC Golf.Horse challenge featuring Tom7 remixed by Tom7.org Foundation. 250
plus a cool $6 million.
Golf.Horse challenge sponsored by Golf.Horse Service of Teach How LLC. And we would like to officially bring the prize pool here. This is 250 million.
In case you doubted us, this one has 0.000009. No, we got to keep it refrigerated.
No, we got to turn it over.
Oh, yes, that's a cool $6 million.
Yes, so that's the prize pool. And if we put them together, well, we don't want to, okay.
We're going to keep this one.
Okay, we'll put them near each other. But then we can, there we go. So that's the prize pool. We're going to put that in escrow with sort of a tepid 256 million. We'll put that in escrow with the Sigbovik Organizing Committee for next year. And so if you think you want to take a crack at that prize pool, it's a large prize pool, moderately warm. Yeah, it's the biggest prize number ever offered.
That's a lot of zeros.
That is a lot of zeros. And in fact, because these are numbers, you could put a lot more zeros on it. On the other side, too. You could, yeah. Zeros all up in this. Let's see. I guess I wrote a little TXT file about this as well. So That's how you can get in on this prize pool.
Golf.horse is a website, so
Oh yeah, good
you're
point.
used to seeing like .com and so forth.
Yeah, golf.horse.
That's just to be clear. That's Jim's thing. But it's like real, and you can go there. You'll see, I was once I was ahead of this. I could have won my own pool 6 million, but David Renshaw is currently the leader. No one has tried the Pokemon yet.
These have been brutal, but there's new word lists coming out, and I think they're going to be exciting. David Renshaw, do you have anything to say to your competition?
Just easy. It's not that hard.
Just easy. That is the word.
Makes it look easy.
All right, thank you. Yeah, if you have questions about this, just send an email to me or someone. Or write them up in your paper next year.
All right. So, are you guys ready to go?
Oh yeah.
Oh, okay. All right. So, our final presentation.
We need some volunteers from the audience. Yeah. We need yeah. You come on up. Yeah.
I don't know this
right
guy.
there. Come
I've
on
never
up.
met
Come
him
on.
before in my life.
Yeah, over there. Come on. Anyone else? Yeah, you right there. Come on. Are people in this room familiar with Family Feud? This will make a little bit of sense. If you're not familiar, it will make a little bit of sense. We've got, okay, anyone else? Two more. Yeah, you, come on. One more. Come on, don't let me down, One more person. Yeah, come on. Okay. So the way this is gonna work is we polled, like 100, 1,000, 30 people. We asked them a number of questions, what's your favorite room on campus? What the goal of these teams is going to be is to guess what people thought the best answers were. You are a team. What is the name of your team? You have 5 seconds. 4, 3, 2.
Sure.
Greg, your name is Team Greg?
No, Team Red.
Team Red, okay. 5, 4, 3. Polka dots background. Okay, are those names any good? No, you are Team GIF, and you are Team GIF. What's your team name?
GIF. Team GIF.
And what's your team name?
GIF.
Okay. Great. So this is gonna work. Where are the buzzers? Where are the buzzers? No, the
Oh my god, did my background.
very important. This is very important.
Extremely important.
Okay. So one person from each team needs to come up. Great. Okay. One person from each team needs to come up. Come, pick one. One. You. Now. Go. Ow! Great. Okay. One. Okay. So it's going to work. I'm going to. Jason actually is going to announce. Are you ready?
It's there.
Okay. Jason is going to announce the first question, and then one of you is going to buzz in first. And when that happens, you have 5 seconds to give your answer to this thing. If you fail to answer 5 questions, it goes to the other team. Yeah. Okay.
What is the rest of the team for?
We're going to keep doing teams. We're going to keep rotating people in.
Whether they get more people than us.
Yeah, because they can't count. Wait, what? You're off the team. Are we good to go?
You're next. They can get some rest if they want someone.
Okay, are we good?
We're good.
Okay. Jason, are you ready?
I'm
Great.
ready.
Okay,
Alright.
what is the first question?
First question is, what is the internet?
Series of tubes.
You got the number one answer, so it goes to this team. No, you don't do the buzzer yet. Okay. So what's going to happen is I'm going to ask each of you in turn to give another answer to that thing, and if you don't get it, you will get a buzz. If you get if you fail to get an answer that's on the board, it goes to the other team. So you have 5 seconds to give me a thing. What is the internet?
Pit of scumability.
Cats.
Babies.
Okay, other team.
Lawyers.
Go. Okay, you're out.
Lots of images.
Okay, Jason, what are the rest of the answers?
Okay. You have a mistake. A tool. Everything. other people, somewhere.
Cool.
Okay.
Okay. Okay. 2 more people come up.
Wait, why
You.
is our score? Wait, which one's our score?
What team are you?
Yeah. Do you know which team you are? What team are you?
I think
Yeah.
First,
Okay.
tell the difference.
Okay. Good. Come on. Do you have a buzzer? Okay. Okay.
Name something you do when your code doesn't work.
You were first.
You debug.
Number 3 answer.
Okay. Now that was not number 1. You get to go.
Screen.
Saw that.
Go. Wait, what the hell are you doing here?
Release it anyway. Release it anyway.
I don't think I heard that.
Okay.
I'll compile it again.
Back 1 more.
Jump up and down.
Okay.
Stack Overflow.
Bang your head on the table.
Sweep.
Well, that's a good one, but unfortunately.
Okay. What are the other ones?
We have curse and protection.
Okay. Next question.
All right.
You come up.
Next question.
You come up. Yeah. Great. Cool. Okay.
What do you name a variable that doesn't matter?
You were first.
Hi.
I do like single letter. I just call single letter ones together.
Okay. Go.
Variable.
Temp.
Okay.
Boo.
Foo is. Oh, it's not number 1. Okay.
Lard.
Okay, I'm bored. Your turn. Go.
XY, 2 letters.
Didn't have that.
Foobar.
No.
Thing.
Underscore.
Okay. Game over.
Someone's name, or just mashing on the keyboard.
Okay. Who's coming up? You come up. Come on. Next question.
Okay.
Let's go.
I'm going to do this one. What does the H in H box stand for?
Hungry.
You got.
Okay. No, but that was not the one answer. So you get to answer one. Can you beat that?
Hip.
Going right, please.
Okay, your team has control of the board. Go.
Horizontal.
And that's the number 1 answer.
Holding.
What was that?
Holding.
What?
Holding.
Oh, holding. Now.
One more. Oh, actually, your turn. Go.
Hurt.
Is that on there? Okay. Go.
Fuck.
Harry.
Okay. Great. Hurry.
Okay.
Next question.
Last one?
Sure, I don't know.
Okay. Chicken.
No, you're overdone. Is there still going?
Chicken.
Yeah, you're off. You won by default. Pikachu.
Oh.
Pikachu. Oh.
Good answer, though.
Chicken.
Wait, say it again?
He said 4.
4 chickens. Yeah.
Okay, your team has control of the board. Go.
Chicken.
Sorry.
Chicken.
Back to you guys.
Chicken.
Chicken.
Last one.
Bacon.
Oh,
Good. Anyway, what are the rest of the answers?
we have buffalo. Common game.
Okay.
So after, wait, no, something has gone wrong with the scores.
Horribly wrong. Or very right.
How is Akiva?
Yeah.
How is Team JPEG doing?
They won.
Oh yeah, okay.
Do we have any questions for our presenters?
I'm sorry, there was no Team Jeff. Chicken.
I had some bonus slides, but they definitely
What is your mother's maiden name?
Chicken. Shut up!
Alright, so we have now concluded the presentation portion of the, I think it's evening now. It might have been the next morning, I can't really tell, I fell asleep. But without further ado, it is my pleasure to announce the chair of Sigbovik for our awards today, Jenny Lin.
I'm Jenny. I'm going to give out awards. But before I do that, I'm going to ask people who are part of the award list to maybe get ready for the cake. Because there's plates, but they're on the floor. And I don't want people rattling around on the floor trying to get utensils and stuff. Thanks, Charlie. There's a lot of certificates. And I'm going to read them, and maybe people will be here to come pick them up. But don't worry if you're not here and you win an award, because we'll probably mail it to you, and I won't just keep it in my office forever. So the first award is most frighteningly like real research, because if you're doubly real, maybe you shouldn't be in this conference, but we took you anyways because we like you. So the most frighteningly like real research award goes to Need More RAM. Just Invent Time Travel by Robert Andrews, Michelle Jones, Patrick Lynn, and the UIUC Theories Yes. If anyone is here from that set of people, come get this piece of paper. Otherwise, I will definitely mail it to you. Okay. The next award is the Best Picture Award, because you gotta have a Best Picture Award. And that goes to Optimizing the Sacrifice. I'm just doing great today. Okay. Nice. Okay. This next one is the Most Likely to Void a Warranty Award, and it goes to Precise ECG Platform on Modern Processors by S. Normalizing Fluke and Ivy Ridge and Skylake. All right? Here. I like awards. Oh, I know for a fact that this person isn't physically here unless they lied to me, but they are here in spirit. So this is the Sigbovik 2019 Congratulations Award, I guess, for 93% of paint splatters are valid Perl programs. This will also definitely live in your possession. Next up, we have the Draw a Code Doc Award. Draw a Code Doc. On double-sided QR codes. I know, it's late. We're all tired. Oh, this one is the most least Czech references, reference non-zero. And this goes to Honest NN and Honest Neural Network Accelerator. See, we knighted Tim, so he's Sir Tim the Honest now, and actually present to receive the award, so it's a Czech. Next up, we have the People's Democratic Choice Award, as chosen by me, the most democratic person in this room. I'm going to give it to not Isaac. Isaac could come up to get this would be
Hey,
great.
that's Isaac.
You'll give it to not Isaac, don't worry.
We'll make sure this ends up in your possession. Here we go. Next up, we have Most Undefeated. This goes to Travis Hance for his
Almond agreement by combat, or whoever defeats Travis in combat.
Well, then I win by default because I actually was fighting him and I won. It's the Sigbovik Best Paper Award, which means, oh, it's a little hard to see, but it's the best paper. And what I do is I take this poster board and I kind of shake it a little bit. Oh no, everything came out and I can't give them all one. And then I just sort of look away and do this, and I pick up this piece of paper. And it goes to which ITG step charts are the bracket jumpiest, in which they milk the boring follow-up paper to which ITG step charts are the turniest, titled which ITG step charts are the cross-overiest, and or foot swishiest series for all it's worth. See, I'm not lying, because but that's fine. I think that's all the awards just sitting over here. And now Sigbovik is mostly over until you eat cake, and then it's really over. So go eat cake, guys. I wanted to thank all of the people who worked really hard to make this happen. Mostly me, definitely. I was doing all lots of other people, like, I don't actually want to bother saying them all. But there's lots of other people, and you should also come help, because then you'll also